for inviting me to give this talk. It's a great pity that I can't be in Torino. It's been a wonderful meeting, and since I'm the last speaker, I thought I should begin by thanking the organizers for arranging such a beautiful set of talks, which were not only incredibly interesting, but they were presented with very, very clear style. And I learned a lot. I want to thank Volodya in particular, who gave a brief overview on Wednesday. And by doing that, he saved me from having to feel that I should be doing it, because I'm certainly not nearly as appropriate as he is to do such a thing. So if I was in the hall at this moment, I would ask everybody to clap for the organizers, but maybe a bit of virtual clapping. So let me now begin my talk. If I can share the screen. Right. So I'm going to talk about the n=4 theory, which of course is a theory of great interest in the context of integrability. But my talk will not be emphasizing integrability. It will be emphasizing supersymmetric localization, which is somehow related, but I mean, if anyone can tell me exactly how, I will be very interested. Now, my screen isn't moving. Oh, there we are. So I'm going to talk about how supersymmetric localization can be used to determine some very precise and very complete data on correlation functions in n=4 super Yang-Mills. These correlators, of course, have been studied a huge amount in the last, at least for the last 20 years, probably. But the ones I'm going to be talking about are not correlators with the operators at fixed positions, but correlators integrated over the positions of the operators with a specific measure, which I'm going to mention in a minute. And this is ongoing work that has been that I've been involved in recently, and other people started some years ago. So the point about this is that although these correlators are integrated over the positions, and therefore a lot of the detail of the correlators is averaged out, that leaves the a function of the coupling constant and of the, in fact, for SUN, of a function of n, which has some very interesting properties and makes clear, for example, its duality property, S-duality. We're able to expand to arbitrary order in perturbation theory and reproduce some very striking features of the perturbation expansion, and also non-perturbative features. And the large n expansion, sorry, I should have stressed that this function of the coupling constant in n is a function that we know for all values of n and all values of coupling. So we can continue to large n, and we can reproduce, well, we can produce a large n expansion, which reproduces facts which are known from earlier work, but also goes further and reproduces a lot of new facts. This is work which, most of what I'm going to say is work done with Daniel D'Aragoni, who's at Durham, and Konkar Wen, who is at Queen Mary, although in present days, it doesn't really matter much where people are, since we can't actually meet in person. We published 2 interrelated papers a few months ago, and most of what I have to say will be the content of these papers. But these are papers which continue from earlier work that I and Konkar were involved in with Shai Chester, Suvi Pupu, and Yifan Wang, where we were looking specifically at the large n limit in a limit which demonstrates the SL2Z invariance of the correlators. But that itself was based on the original work by Binder, Chester, Pufu, and Wang, who set the ball rolling some years ago with their work on the large n limit, the Tuft limit of these correlators. So let me say briefly this is, of course, a sort of telegraphic talk, because I can't possibly go through many of the details. But let me, well, actually, let me also say, if you can't hear me, please let me know, because in the past I've had trouble with the microphone on my computer. So I'm going to give a very brief review of supersymmetric localization in this particular context. So the localization you start with the n equals 2 star supersymmetric Yang-Mills theory, which can be thought of as a mass deformation away from the n equals 4 limit. The n equals 2 star theory has a massive hypermultiplet in the adjoint representation, but if you let its mass go to 0, then it becomes n equals 4 supersymmetric. And we're going to discuss the partition function, actually the Pestun partition function, which many of you, and possibly most of you, are familiar with, which is defined on S4. In the end, we're going to transform to R4, but that, for what I'm going to say, that's not going to be, I won't even mention it except in passing, because it's rather straightforward. Pestun, in a classic paper in 2008, evaluated the partition function of the n equals 2 star theory, or the n equals 2 theory in general, on S4. And this is his expression. Localization reduces the partition function to a multidimensional integral over the Lie algebra of SUN. So it's in the end, you look at the you integrate over the eigenvalues of SUN matrices, and so the n-1 variables to integrate over. And that transformation to the eigenvalues gives you a Vandermonde determinant. It's a Gaussian matrix model. And there are two important factors. There is the first factor, which I've called Z-PERT, is it comes from the one loop determinant of fluctuations around the localized solution. I'm not going to write it down in detail. It's a very specifically well-defined function involving the Barnes G function, which is just, there's no point me writing it down here. And the instanton part of the partition function, which plays a crucial role in what I'm going to say, is the Nekrasov partition function, which can be, which describes instantons, in fact, localized at the north and south pole. Sorry, instantons at the south pole and anti-instantons at the north pole of the S4. And Nekrasov gave a beautiful but incredibly complicated prescription for calculating quantities using in this partition function. And it is a complicated sum over, in general, of Young diagrams. In the limit that you take the mass to 0, in the limit that gives the n equals 4 theory, the partition function itself becomes trivial. It becomes 1. But we are not interested in the partition function. We're interested in correlation functions, which are derived by taking the partition function with the mass not equal to 0 first, and then, as I'll show in a minute, that can generate correlation functions. So the kinds of correlation functions we're going to talk about are correlation functions of primary operators in the or superconformal primaries of the stress tensor multiplet. Often called O2, and O2 is the trace of phi squared, where phi is the 6-component scalar field in the n equals 4 theory. And there's a standard way of extracting the SU4 quantum numbers in terms of this null vector y, which won't play much of a role in what I'm going to say, but that's the formula for the O2 operator. And we're going to be interested for most of the talk in this operator, although at the end, if I have time, I will say slightly more general things. And we'll be interested in particular in the 4-point function of 4 O2s, which I've reproduced the standard sort of way of writing it here. It's split it into a free correlator and another piece, which is where the interactions are encoded, and that piece itself you can factorize out the bit which depends on y factors out. And so in the end, the interesting piece is this Tn which is which encodes the dependence on the cross ratios U and V. So U and V are the standard cross ratios, which are defined in terms of x1, x2, x3, and x4 in a standard way. And we're going to be talking about an integrated correlator. So that we're going to take this correlator, this expectation value, and we're going to integrate it over U and V with a specific measure. The point is that the correlator itself, the partition function, is of course supersymmetric. Any correlator is not supersymmetric if you fix the positions of the operators, because they depend on the positions, and therefore the super algebra they will not be invariant under the supersymmetry transformation. However, if you integrate with an appropriate measure, you will get a quantity which is invariant. So this is the quantity we're going to talk about. It's a function of n, of course, the n of SUN, and it's a function of the coupling constant. And I put an index I here to indicate that there are several different, there might be several different correlators to consider. The two that we have in the past looked at, I've called G1 and G2, and I've written them down just to show explicitly what this measure is. For G1, it's R sine squared theta over U, and for G2, it's got an extra D function or box diagram in the measure. There are almost certainly other measures that one could consider, but in fact, one of the questions at the end is about that issue. But for this particular talk, I will actually only be talking about G1 because that's what the content of our paper is. We're working hard on G2, and we will hopefully soon have some results on that. So why do I like these correlation functions this way? Well, they are related to the partition function. So this paper in bold, listed in the middle of the transparency, Binder, Chester, Puffer, and Wang, I think it was early 2019, that showed that you get the correlation functions of this type by taking derivatives on the log of the partition function. So what I call G1 involves 4 derivatives on the log of the partition function, 2 with respect to m, the mass, and 1 with respect to tau, and 1 with respect to tau bar, where tau, remember, is the coupling constant. So this is the correlation function which I'll talk about in this talk, mostly, until the end. And then the second correlation function involves 4 derivatives with respect to m, and it's considerably more difficult and more complicated to decipher what its content is. So I won't be talking about this except in the comments right at the end. This correlator G1, which I'm going to call G from now onwards, is complicated to analyze anyway. What we did was we expanded, we looked at the perturbation expansion for this correlator. I should say the earlier work was all focused on large n, and we wanted to look at the function as a function of n as well as tau. So what we did was we did some detective work. We considered a large number of values of n, and we looked at large numbers of terms in the perturbation expansion with the help of Mathematica, of course. And then, but it was crucial for us to understand the instanton contributions. And we had already looked at the instanton contributions in our earlier paper with these other people. And we had an expression for the, an explicit expression for the one instanton contribution for many values of n, and then a not quite so explicit expression for the k instanton contribution. This involves a large number of manipulations with a Nekrasov partition function. And what turns out to be the case is that the decomposition, the expression in terms of the sum of Young diagrams simplifies in the m goes to 0 limit in a dramatic fashion, such that the Young tableau, the Young diagrams that contribute, instead, you could in principle have a Young diagram for every value of from 1 to n, every location between 1 and n, but actually the only diagram that contributes, at least for the first correlation function, is one in which the Young diagram is entirely in a single location, and it is essentially rectangular. It describes an instanton of instanton number k, where K is P times Q, and P and Q are the side and the length of the Young diagram. It's not quite saying it's rectangular isn't quite accurate. It's rectangular up to some statement which I've called partial transpositions, but I'm not going to describe that in my talk. I just wanted to clarify what happens when one looks at the m goes to zero limit, simplifies the analysis. Anyway, putting together, looking at the patterns that came up from this decomposition, enabled us to come up with what in fact is a rather, now unfortunately my transparency, my slide's not, it's not changing. I think I'm going to have to stop sharing and start again because I can't. Oh no, it's changed. Good. So we ended up with an expression for this integrated correlator, which is remarkably simple in its structure. It's given by a double sum. It's a sum over a two-dimensional lattice, sum over two integers m and n, with this exponential factor e to the minus pi t m plus n tau squared over tau 2, integrated over t with a weight determined by a function of t, which we call bn. So the n dependence, the n, remember, is the n of SYM, enters entirely in this function bn, and the essential part of that function is in the numerator, there is a polynomial in t of order 2n minus 1 with rational coefficients. This structure makes SL2Z completely manifest. It's very simple to see that this sum and integral transform is invariant under SL2Z. The SL2Z, of course, is needed because this theory is invariant under Montonen duality. This is the duality that's the holographic image of the S duality in the type 2B superstring, which is also SL2Z. This function B satisfies certain conditions, the most important one being that it's actually got an inversion symmetry, the type that I've written here. It also integrates to a constant, it depends on n, and there's another condition I've written, that the integral of b over root t vanishes. Examples of this, for SU2, b is this cubic polynomial divided by 1 plus t to the 5th, and for SU3, it's a quintic polynomial divided by 1 plus t to the 7th. We have for general n, I'm going to show you what the result is. It's extremely it's not particularly beautiful. It's given by the polynomial q is given by the sum of two terms, which are each polynomials in t, or powers of t multiplying Jacobi polynomials. So it's got a simple structure, but it just looks complicated on the screen. But so we know this function for all n, and we know it, and it also describes all tau. So we can look at this function gn of tau and tau bar. We can look at it in any region of parameter space that we want. So for example, we can look at the Tuft expansion, the perturbation expansion for small coupling. I'm sorry, and now for finite n. So I'm going to start with finite n. So the Tuft expansion is an expansion in powers of g squared n, which we've normalized to 4 pi squared. So the parameter a is essentially the Tuft coupling. The expansion is complicated, of course. I mean, it goes on forever, but this is the first few terms. And these few terms immediately show you interesting structure. So this is a sum of coefficients I've gone up to genus 7, or 7 loops in Yang-Mills. The features that this shows, unfortunately, every time I try and change, I can't get to the next bit of transparency. well, I can say what I know is coming up next, which is that the expansion is an expansion in which each successive power of A has a coefficient that's a zeta value. The zeta values are odd zeta values, which depend on the loop order we're talking about. The first three terms don't have any dependence on n. They are essentially planar, but at four loops, there's this term with 1 over n squared, which indicates the first non-planar correction. And then at 5 loops, there's a non-planar correction. At 6 loops, there's 2 non-planar corrections. At 7 loops, 2 non-planar corrections. And I stopped at 7 loops because up to this order, this is what is known from Yang-Mills perturbation theory, that the non-planar contributions start at 4 loops, and there's this pattern which goes on forever, of course, but it's very difficult to analyze Yang-Mills perturbation theory. It's extremely difficult, of course. If I could only show the rest of this transparency, which I am having trouble with. I don't know what to do. These coefficients, the precise coefficients, are precisely up to the order in which Yang-Mills has been calculated. These are precisely the coefficients you get in Yang-Mills. Of course, in Yang-Mills theory, you don't get numbers. You get the horrible looking, if you calculate it. Hello?
Hello?
Yeah.
Could you please stop sharing and then try again?
I will do that. Thank you.
Yeah.
I was thinking I have to do that, don't I? Right. Try again. I better stop sharing and stop my my presentation as well, shouldn't I? Ah, this is stupid. No, I'll try again. So far, oops. So far, so good. Okay, so this is where I was. So the coefficients of rational multiples of zeta values, the unintegrated. If I didn't integrate, then the correlator would look very complicated, of course, because it's got logarithms and dilogarithms, polylogs at every order, getting more and more complicated. But the amazing thing is that when you integrate over the cross ratios with the measure I mentioned, that kills all the complications, and everything reduces to a sum of ordinary of odd zeta values. And to see this, we actually used some old papers which I wasn't aware of, where people had integrated analogous diagrams, and we saw how the systematics went. But this is a quite remarkably simple formula. And it may or may not be of interest to people in integrability to know that non-planar corrections come in at 4 loops, and that there is a systematic way in which they continue beyond 4 loops. This function actually satisfies another remarkable equation, which is that because Bn itself has, I'm not going to show you the details of this, but because it satisfies a second order differential equation, which relates Bn to Bn plus 1 and Bn minus 1, the correlator itself satisfies such a differential equation, which is a recurrence relation. So the Laplacian on Gn relates Gn to Gn plus 1 and Gn minus 1. This is the hyperbolic Laplacian, of course. And now again, I'm in the same trouble. I can't move the. I'm sorry, I'm going to have to do that stopping sharing again. Right. I don't know if this will keep working, but anyway, since it turns out G1 is 0, then given the SU2 case, which is G2, this equation determines G3 and so on. So it's iteratively, you can determine the value of G for any value of n. And furthermore, it's easy to, well, it's not so easy, but one can discover.
Sorry.
Yes.
Michael, we can't see the slides. Could you?
You can't see the slides. Oh, dear. I can see the slides, but that's not particularly useful. Let me. Now you can see that, right? Let's see what happens now. Well, for the time being, it's working again. Can you see that?
Yes.
Yeah. So it turns out that this equation and actually the structure that the function I showed earlier, this function is satisfy that you can rewrite it, at least formally, as a rather interesting expression in terms of non-holomorphic Eisenstein series. So let me quickly review what a non-holomorphic Eisenstein series is. It's a modular function. So more generally, a modular form transforms under SL2 by this factor, this C tau plus D to the W, C tau bar plus D to the W hat, where W and W hat are holomorphic and anti-holomorphic weights. So that defines what's meant by a modular form, where the weights are non-zero. When W hat is minus W, then the prefactor is a phase. And right at the end of the talk, I may talk about the correlators where this phase transformation is non-trivial. The phase defines a U1 charge, Q, which is defined to be twice W. But for the moment, the O2 operator, the one we're talking about, has zero weight. It's invariant under modular transformations, and the correlation function is invariant. And in fact, it's going to be expressed in terms of Eisenstein series. These Eisenstein series are given as double sums of this standard type. Tau 2, remember, is 1 over the coupling constant. Tau 2 to the s divided by m plus n tau modulus to the 2s. That defines the Eisenstein series, which in fact is periodic in tau 1, and it has Fourier modes, which I've called Fk. The zero Fourier mode, which is the piece that contains the perturbative terms, has two perturbative terms. It's got a tau 2 to the s, and it's got a tau 2 to the 1 minus s, where tau 2 is, as I said, 1 over g squared. So that's where the perturbative terms will come in. The non-zero modes are given in a standard way, in fact, by basically the proportion to k Bessel functions, with an interesting number theoretic coefficient, the divisor sum. These Bessel functions, of course, have an asymptotic behavior at weak coupling or large tau 2. They behave like e to the minus 2 pi k tau 2, and that's characteristic of instantons. So the non-zero modes contain instantons, and the zero modes contain the perturbative terms. And then the standard thing about Eisenstein series is that they satisfy Laplace eigenvalue equation. So this E satisfies a Laplace eigenvalue equation. And in fact, it's the unique solution of such an equation if you assume boundary conditions, which are SL2Z. So E is an SL2Z invariant function, a modular function. Making use of these E's, it turns out you can rewrite the expression for Gn as a linear sum of an infinite number of E's. So there's this rather beautiful but rather formal equation here that Gn is given by an infinite sum with coefficients Cn of s multiplying the Eisenstein series Es. And these coefficients are determined by Bn in my earlier formula. You expand Bn in powers of t, and that gives you the coefficients Cn of s. And using this formula, you can actually read off a lot of interesting things, particularly about the instanton sector of the integrated correlator. For SU2, as an example, these coefficients C2 have this form, and if you wanted to read off the perturbative piece of G, well, remember each Eisenstein series in that sum has two perturbative terms, one of which is tau 2 to the s, and the other is tau 2 to the 1 minus s. Well, only one of those can possibly be small in the perturbative limit. G2 to the second one, tau 2 to the 1 minus s, if s is positive, which it is small when g squared goes to 0. The other one appears to be large, and you'd think that when you summed up an infinite number of large values, you'd get an ill-defined expression. But actually, it's Borel summable, and when you resum the terms, you find that the two contributions, the tau 2 to the s contribution and tau 2 to the 1 minus s, are equal. They each contribute half the value of the perturbative terms. The instanton contributions can be read off as well, and I haven't got time to go into it, but you can write an exact formula, which for SU2 has this rather simple form. Y here is proportional to 1 over g squared. So the perturbative expansion, again, looks like an instanton contribution, e to the 2 pi I tau, with an infinite set of perturbative corrections. I've written, for what it's worth, the general, this solution for the K instanton solution for general N, which can be written down reasonably straightforwardly. So all that, so far I've only talked about the weak coupling expansion. The small n expansion. For large n, you can now look at the asymptotic behavior of these coefficients, and you find that the you get a Tuft expansion, the topological expansion of Tuft, where you get a power series in n, where little g, the sum is the sum of the different genus, and each function, capital G with superscript little g, is a function of the Tuft coupling. Of course, in this Tuft limit, the one I'm looking at right now, you lose the instantons. But this is something which is rather familiar if you look at the planar. The leading term is the planar sum of planar diagrams, and this gives a precise sum of planar diagrams with in the small lambda perturbation expansion. This expansion, in fact, converges for lambda less than or equal to pi squared. But it can be resummed. It's Borel summable, and you can rewrite it as an integral over with a hypergeometric function and divided by a sinh squared, and that reproduces the line above in the small lambda expansion. But you can then read off the large lambda expansion from the same sum, and you get this expression here for large lambda, which coincides with an expression that was written down by Binder, Puffer, and Chester and Wang. But they were only looking at the large lambda expansion, and they were not considering whether this was convergent or not. This is in fact not convergent. Actually, I forgot to put the symbol, the sum symbol. Obviously, it has to be summed over n, and then it's not summable because the Borel transformation has there's a cut in the Borel plane, which is an indication that it needs a non-perturbative completion, non-perturbative in lambda, and we can work out precisely what that non-perturbative completion is using modern techniques. And the non-perturbative completion gives a series of terms which have instanton-like behavior. But here, these are instantons not in Yang-Mills instantons, but these are terms of order e to the minus 2 root lambda, which is an indication when translated into string theory language. It would be an indication that the dual string theory had some sort of instanton-like, a worldsheet instanton contribution to this correlation function. We haven't actually understood exactly where. I mean, although it's clearly a worldsheet instanton, we have not understood in great detail this structure. And then this is just for the planar diagrams. You can go on and do the first non-planar, second non-planar correction, and so on. It's not that difficult to look at the higher non-planar corrections in this limit. So this is the Tuft expansion at small and large lambda. More interesting, perhaps, from our point of view, was the expansion where you fix the Yang-Mills coupling constant instead of the Tuft coupling, because that doesn't suppress the instantons. And then you get an expression in the large n expansion that is invariant under S duality, SL2Z. And that's related directly to known facts about the low energy expansion of the type 2b superstring amplitude, which has been studied for some years, at least in flat space. But here, I mean, the virtue here is we're talking about the expansion in AdS5 S5. So although the flat space limit is very interesting, it's probably more interesting not to take the flat space limit. And so we get this by looking at the expression I had earlier for the correlator, which had this function Bn of t. Since we know Bn, we can look at the large n expansion, and this is the solution that you get, the expansion that you get in the large n limit with fixed G string. So here again, you see that there are terms which, well, the leading term is of order n squared is a supergravity term. The next term of order n to the half is a coefficient that in string theory would be associated with r to the fourth. And then the next term would be associated with d to the fourth, r to the fourth, and so on, except these aren't the string theory amplitudes. These are, this is the large n limit of the Yang-Mills correlation function, and the precise connection with string theory is not that easy to make. But so I made some comments here. This is the Eisenstein series now are half integer index. Earlier, I had an infinite series of Eisenstein series for when I had n fixed and not large necessarily. But now I'm looking at the large n expansion, and the Eisenstein series are now half integer, and they have somewhat different properties in important ways. As I said, there's a close connection to string theory, but the closest connection is for the first three terms, because those terms in string theory are BPS terms. Higher order terms in string theory in the low energy expansion are not BPS and are not expected to take particularly simple forms. But these first few terms are BPS, but it is notable that the last BPS term in string theory is of order d to the sixth r to the fourth, and that would come in with a coefficient of 1 over n, which is not half integer. So this correlation function, this integrated correlator, doesn't get all the information. I said earlier that integration washes out information. Well, here it's washed out, for example, the presence of the d to the sixth r to the fourth term. And the other correlator, the one which I am not really talking about, is, but we've looked at, that does contain that d to the sixth r to the fourth term. Right. I've still got some time, so let me, I wasn't sure if I'd get to talk about the next topic. I will flash through two transparencies on work that I've been doing, well, firstly with Concal Wen and secondly with Daniele Dorigoni, where we've extended this work on U1 violator, on these 4-point correlators to look at correlators with more than 4 points, but there are other special correlators. So let me remind you that here I've drawn the stress tensor supermultiplet. So O2 is at the top of this pyramid, and that's the operator I've been talking about so far. It's a primary operator. But if you operate with supersymmetry transformations, you can work your way down the multiplet. And in particular, there are two operators I want to emphasize here, the one I've called lambda and the one I've called O tau. Lambda you get to by three steps, three supersymmetries acting on O2, and O tau by 4 supersymmetries. These now carry non-zero U1 charge. They carry non-zero modular weight. The modular weights, the modular weight of O tau is 1, and of lambda is 3/4, at least in my units. And that means when you take correlators, these correlators will violate the U1 charge. Well, just as I was saying this, I've again failed. I can't move the screen.
Michael, could you try this, the left, the lower left?
Can I try one?
This is arrow, the lower right corner. Yeah, there's.
That's what I'm doing. That's precisely what's not working, unfortunately. I don't understand why. It's presumably my fault.
The keyboard.
I'm on the key. I'm using keyboard, and I'm. But I shouldn't. Maybe I should just use the pad. So this U1 in the Yang-Mills theory is called the bonus U1. At least that's what Intriligator called it many years ago. And it's a broken U1, which has a certain. And there's a certain pattern to the U1 violation. So that pattern is that for all the 4-point correlators that you can make conserve U1. Endpoint correlators in general violate U1 but the violation is bounded by, in my units, by 2n minus 8. And that means that there's a maximum violation, and the maximum violation is 2n minus 8. And there's some interesting correlators. So what we've done is we've generalized the previous work I described to discuss these correlators that violate U1 maximally. And the two examples that I've put up here are, for example, you can have 16 lambdas. 16 lambdas is has got a W of 12 because each lambda is 3/4, and you can also have, that's one possibility. And then there are possibilities, in particular, the ones which are easiest to discuss are the ones where you add O tau. This is O tau members of chiral Lagrangian. So you take a correlator with 4 O2s and then add any number m of chiral Lagrangians, and then you get an m plus 4-point correlator. And then you integrate, and we're going to integrate over all, instead of integrating over x1, x2, x3, x4, we now integrate over all the x's. And we want to construct the analog of Gn, the analog of what I had when m was 0, but now with m not 0. And for that, you have to just use a covariant derivative. There's a covariant derivative which increases the value of the modular weight by 1, of W by 1, and it decreases the anti-holomorphic weight by 1. And so D acting on F does what it says on this transparency. And then you can define a conjugate D bar, which decreases the weight by 1. And then you discover that the correlator, the second correlator I have at the top of this transparency, the one with M O taus, is given simply by taking covariant derivatives on the original correlator that we had before. I won't go into that in any more detail. Time is almost up, and I've got a few odd comments here about that, but they're not really particularly important. They are, I mean, we've studied the perturbation expansion and the instanton contributions to these correlators. So finally, I've got a number of small comments and, well, questions mostly. So we've determined the functional form of this integrated correlator that you get by a particular 4 derivative acting on log Z. And we found that it has a lot of information about the functional form of the n dependence and the tau dependence, even though it doesn't have much, it has no information about the position dependence. I didn't discuss the second correlator. What in the literature, as far as I know, the only discussions have been by, firstly, actually by, I think by Binder, Chester, and Kufu, but also we looked at the large N expansion at fixed G Yang-Mills in an earlier paper, and we found the statement I said earlier that the term of order d to the 6th after the 4th comes in at order 1/n. And it's instead of being an Eisenstein series, there's this other kind of series which have come up earlier in string theory, where the function E satisfies a Laplace eigenvalue equation, but with a source term on the right-hand side, where the source term is quadratic in Eisenstein series. So this has a very rich structure, which I haven't got any time to go into. There's a bit of a puzzle here, however. If one wanted to discover the flat space limit of the terms that we know are the terms in string theory, we don't have enough information to discover, we've got two correlation functions, but it turns out that to pin down the d to the sixth after the fourth term, with its precise coefficient in the flat space limit, you need 3 correlators. So there's a suspicion that there's another localized correlator floating around somewhere that we have not studied. We thought that it had something to do perhaps with looking at Pestrin's analysis on a squashed force sphere and then taking a derivative with respect to the squashing parameter, but that doesn't seem to generate an independent correlator. And then there are lots of other questions I could go into, but I won't, about how this might extend to other models, such as the ABGM model and models with other gauge groups. But there is one more question, which is perhaps the most relevant for this. I don't know the answer to this question, but many of you might, whether there are connections between any of this supersymmetric localization for correlators and results which come out of n equals 4 based on integrability. Anyway, that's all I have to say. I want to repeat that I am extremely impressed by this conference, and it must have taken some organization given the circumstances. So many thanks to the organizers. And I tried to buy some Italian ice cream yesterday whilst you were having your banquet, but I couldn't find any. So anyway, thanks a lot. So
thank you very much, Michael, for the beautiful talk. So no? Yeah. No, it's on. Yeah. So any questions? Yeah.
I can see one online. Oh, no.
Okay, well, thanks very much for this beautiful talk. So you said, if I understood correctly, this d to the 6 r to the 4 term in the Young-Mills calculation dropped out after you took this integral. Can you understand this directly from the 2B supergravity perspective, that this contribution would drop out?
No, that's a very good question. I'm sure that it should be possible to understand it, but we haven't. In other words, doing the integrating with a specific measure in the Yang-Mills must correspond to doing something very specific in the supergravity, but we haven't sorted that out, I'm embarrassed to say. So the d to the 6 after the 4th dropping out means that certain coefficients cancel. Then it comes into the second correlator. So that there are 2 pieces of information. The fact it drops out of the first one is one piece of information. And the fact that it's got a particular coefficient in the second correlator is another piece of information. But in order to pin down its value in the coefficient in the string theory, you need a 3rd piece of information. And that we haven't done.
Or more generally, you need to understand how the X dependence of the super Young-Mills appears from the worldsheet perspective. So you can understand what integrating in super Young-Mills means from either the worldsheet perspective or from supergravity. So there must be some way of relating the X dependence back to supergravity, right?
Yeah, absolutely. Yeah, I think you're right.
But I mean, do you see structurally what this could be? Do you see some sort of hint of how one could implement this X dependence from sort of the string or supergravity perspective by some, I don't know, some differential equation it has to satisfy, or some sort of structural property?
Not that, no, we haven't. I don't know. I can see one of my collaborators with his hand up, so maybe he knows. Concau. Can I ask Concau to? No.
Right. Yeah. I maybe I can add some comment. I think Michael said most of it. So for for D6 out to the 4, or even out to the 4, D4 out to the 4, because they are contact interaction, it's easy just to write out the milling amplitudes for those correlators. Right? As Michael said, for D6 out to the 4, because the 6th derivative translated into milling space, this were like S to the Q, S square, and constant. So therefore, there are 3 constants to determine. We do know the space-time dependence in the sense that we have bases, S to the Q, S square, and the constant. But the coefficient is unknown. So as Michael said, we have 2 conditions. We are not able to fix 3 coefficients. Well, nevertheless, one can of course use the flat space limit, which was derived by Michael long ago. So if we use the flat space limit, then we can determine all those 3 coefficients. Or said another way, we determine this correlator as this order.
Yeah, so there's another question from Akani.
I can see Arcades online.
Oh yeah, okay. Yes, hello.
Hi, Arcades.
I have a strange question. So essentially what you're doing, you're looking at small mass expansion of partition function in this n equals 2 star partition function.
Yeah.
M squared, M4, whatever. And so the properties of these 2 correlators, they're inherited from this partition function. So the question which I have is about these exponential corrections, which you mentioned that may be related to worldsheet instantons. Strong coupling is not barrel ensemble, so there are exponential corrections. So from n equals 4 point of view, there's no good reason for any worldsheet instantons. For example, of course, in many other observables, there is no barrel summability at large lambda as well. So for example, in cusp anomaly, there are similar corrections, but they have different interpretation. At least that was what was suggested by, say, some mass gap on 06 model, etc. But my point is that could it be that when you consider integrated correlator, you're actually probing this n equal 2 star partition function, which does have some kind of other string theory interpretation where, like in orbifold models, where you have some S2 in S5, which is special, where you may have worldsheet instanton contributions. In fact, we discussed some examples like that in other n equal 2 superconformal models. So could it be an artifact of this integrated correlator that you see these exponential corrections? Well, you see them, but they don't have worldsheet interpretation, which you are suggesting, because just looking at AdS5 S5 looks like there are no natural candidates for these worldsheet instantons. At least that seems a little bit puzzling.
Right. No, I think what you say sounds very interesting, and which you say you looked at.
Oh, we wrote a few papers with Matteo Beccaria and Gerald Dunn recently. It's about n equal to models, not n equal to star, but other superconformal n equal to models, where the same localization of free energy is known, and you can look at it and study, for example, Wilson loops or correlates, and there are very similar exponential corrections appearing there in strong coupling expansion.